Hey, welcome! Have you ever just stopped and wondered how everything around us is connected? From your group of friends, to the internet, to the power grid that's literally lighting up your room right now? Well, it turns out there's a whole science to it, and if we can understand it, we can explain some pretty dramatic events in our modern world. Let's kick things off with a really powerful example. Okay, so picture this. It's August 14th, 2003. Cities across the northeastern US and parts of Canada are all lit up, just a normal night, everything running like clockwork. Now fast forward just 24 hours. This is what that same area looked like. A colossal blackout that plunged 50 million people into total darkness. I mean, the difference between these two images is just staggering. So that's the big question, right? How on earth could one tiny little glitch way out in Ohio cascade into one of the biggest power failures in history? How can a system that massive be so incredibly fragile? Well, to answer that, we're going to have to learn a whole new language.
And that new language? It's the language of networks. See, to really get why our modern world can have these massive cascading failures, we need to peek under the hood and look at the hidden architecture that connects everything. And that journey starts with an idea called a complex system.
So, what in the world is a complex system? Well, the idea is actually pretty straightforward. It's just a system made up of a whole bunch of interconnected parts. But here's where the magic happens. When those parts work together, they can do things that none of them could ever do alone. Think about it. A bustling city, the human brain, the global economy. Those are all complex systems. And this quote just nails the core idea perfectly. In a complex system, the whole thing is way more than and totally different from just adding up all its pieces. A single brain cell is pretty simple, but you get enough of them together and suddenly you have consciousness. One computer is just a machine, but link them all up and you get the internet. Now, what's really fascinating here is that if you dig into the structure of any complex system, you're going to find a network. The network is the blueprint. It's the underlying skeleton that holds the whole thing together and basically dictates how it's all going to behave. And any network, no matter how complicated it looks, is made of just two simple things. First, you've got nodes. These are just the individual parts. They could be people in your social circle, computers, or power plants. And second, you've got links. Yep, just the connections between them. Simple, right? But here's the kicker. How those nodes and links are arranged, that changes everything.
For the longest time, scientists thought they had networks all figured out. They had a very specific idea about how they were organized. An idea that, as it turns out, was completely fundamentally wrong. So let's take a look at what that old idea was and why it missed the mark so badly. For almost half a century, the leading theory was that complex networks were just random. This came from two brilliant mathematicians, Erdos and Renyi. Their idea was basically that you could take a bunch of nodes and then just connect them to each other randomly, almost like you were throwing darts at a board to decide what gets linked. Now, this random model predicted that all networks are, for lack of a better word, democratic. What that means is if you went and counted the number of connections for every single node, you'd get a classic bell curve. Most nodes would be totally average, with about the same number of links. No real superstars, no total loners, everybody's pretty much the same. It's a nice, orderly picture.
But then, in the late 1990s, scientists finally got the tools to start mapping real-world networks. And what they found didn't just tweak the old model, it completely shattered that 40-year-old idea. When researchers finally had enough computing power to map something huge, like the entire World Wide Web, they were all expecting to see that nice, democratic bell curve. But the data told a radically different story. The real world wasn't random at all.
Okay, so here's where the script gets flipped. While those random networks are democratic, real-world networks, which we now call scale-free networks, are the total opposite. They are completely undemocratic. They're more like a monarchy, where a tiny, tiny number of super-connected hubs dominate the entire system. And they don't follow a bell curve, they follow something called a power law, which is basically a rule that says a few have a ton and most have very, very little. And this right here is the visual punchline. On the left, you've got that neat, orderly bell curve everyone expected to see. But on the right, that's reality. That steep, plunging curve is the signature of a scale-free network. It's a graph that screams at you that most nodes have just a couple of links, while a tiny elite, the hubs, have an absolutely mind-boggling number of connections. Just take a look at this map of the internet. This is not some random mess. It's a perfect example of a scale-free network. You can literally see the hubs, those big, bright starbursts of light. Those are sites like Google or Wikipedia. They're the superconnectors that pretty much hold the entire structure of the internet together.
And if you want a number to chew on, an early study of the web found that over 80% of all web pages had fewer than 4 links pointing to them. Meanwhile, a tiny fraction, less than 0.01%, had over 1,000 links. That's the insane power of hubs.
So what? What does this all mean? Well, this discovery of scale-free networks and their hubs has some massive consequences. It explains both their incredible strength and their shocking weakness. And yeah, this brings us right back to that blackout.
So here's the big trade-off. Scale-free networks are amazingly tough when it comes to random accidents. Since most nodes have very few connections, you can knock them out all day long, and the network as a whole will barely even notice. But, and trust me, this is a huge but, they have an Achilles heel. They are extremely vulnerable if you deliberately attack their hubs.
Okay, so now we can finally solve the mystery of that 2003 blackout. The power grid is a scale-free network. The failure started at a critical hub, a high-capacity power line. When it went down, all the massive electrical load it was carrying didn't just vanish. It was instantly rerouted to its neighbors. But those smaller neighboring nodes weren't built to handle that kind of surge. So they overloaded and shut down, and they pushed their load to their neighbors, and boom, a catastrophic cascade was unstoppable.
And understanding this Achilles heel isn't just for power grids. It is absolutely critical for internet security, right? Protecting the hubs that route all our data. It's essential for epidemiology, for understanding how superspreaders can act as hubs to accelerate a pandemic. This structure is literally everywhere we look.
This whole realization, the fact that the same organizing principles seem to pop up in so many different systems, well, it's given rise to a whole new field of study, one designed to make sense of our deeply connected world.
And this new field is called network science. It's so powerful because it's not just one thing, it's interdisciplinary, connecting everything from sociology to biology. It uses hard math to find the universal laws that govern all these connections. And of course, it relies heavily on computers and real-world data to map out the massive networks that define our lives.
So at the end of the day, what network science gives us is a brand new toolkit. For the first time in human history, we have the tools to not just see the invisible connections that shape our world, but to actually understand them, to predict how they'll behave, and maybe, just maybe, protect the systems we all depend on.
And that leaves us with a really big thought. We are the first generation that can truly see the hidden architecture of our world. We can map the networks of friendship, of finance, of disease. So the real question isn't what we found, but what are we going to do with this new vision? How will seeing the invisible change our future?